as it was mentioned, I worked for some years at the University of Texas Applied Research Lab, and I basically started in physics but switched to electrical engineering, took a lot of signal processing courses, and worked in an area in acoustics that did not have off-the-shelf instrumentation. We had to build our own instrumentation. In the late 60s and early 70s, we started using computers with digitizers to build our instrumentation. And that would really set an idea for vision for a new way to do instrumentation. So here we are some years later, where we've really built this into a company with over 6,000 employees, around $1 billion in revenue. We'll be talking about that in the future, exactly what we're doing. And one of Fortune 100 best places to work for 12 consecutive years. We call our approach a virtual instrumentation approach. It's this combination of hardware and software, where the software really is, we say the software is the instrument. So it's a very software-centric world. And of course, we know that's the way a lot of the world has gone. Our smart mobile devices are very, very software-centric as well. It is about the software and creating this environment that really allows you to significantly quicker create very advanced application. And now we're taking on some of the hardest applications around to demonstrate that fact, where we have a combination of interface to hardware. You got the analysis libraries, you name it, tens of thousands of analysis functions, custom user interfaces where you can build those very quickly, and then targets you can deploy this on, and then technology that supports multi-core and FPGAs with a very differentiated capability. And then what we sometimes call models of computation, multiple ways of looking at your problem, whether it's text-based with .m code or our icon-based data flow approach. We also sometimes talk about K through rocket science, and we work with Lego and Lego Mindstorms, and we do for 7-year-olds, Mindstorms for 10-year-olds, so we're literally, by abstraction, LabVIEW is actually able to work on creating what Lego likes to call the Christmas experience. You know, when the kid opens up the toy, within 30 minutes they have to be successful. You know, we wish we could all do our experiments that fast, right? And on the other hand, CERN, where we control the collimators around the ring with 10 microsecond motion control. So it is about abstraction. Really, what computer science has done over the years is found better ways, higher levels of abstraction. And we actually work quite closely with another university that's been in this space about the same length of time, looking at data flow as an alternative for building system. That's Berkeley. So we kind of adopted their language to speak about these applications. And this way of programming with data flow and these models of computation. To demonstrate the prowess of this technology, we've taken on some of the toughest programming challenges for real-time applications. The extremely large telescope is, each segment of it's about 2 teraops of performance needed with a 1 millisecond response time. The tokamak control, for first time we're demonstrating real-time control of tokamak, 0.6 second loops we're able to do. And then early detection of cancer with 320 channels running at 50 megahertz each. So these are all extremely complex computation required to do these using a combination of multi-core and an FPGA. Here we see the tokamak where you have 128 CT scanners around the toroid. That's your input measurement device. Then you're solving this control equation and then a feedback loop to control the tokamak. So just showing literally teraops of performance in real time. Here we see the OCT one with those 320 channels, doing some 700,000 FFTs a second across the channels so that we can in real time show a 3D image of a skin for cancer detection. Here we see another, they were extremely large telescope, 1.87 teraops for 1/4 of the computation. We demonstrated this on 64 8-way servers to demonstrate the computation to control 15,000 actuators with a flexible membrane mirror to correct for aberrations in the atmosphere for 4 green lasers that reflect from the ionosphere. So, as I mentioned, it is about these models of computation, creating ways that are more natural for you in programming and developing your system to look at it. Our structured data flow is where we started with LabVIEW. We quickly learned that folks wanted to integrate C code, and as we went to the FPGA, we added the ability to integrate VHDL as well, in addition to generating VHDL directly from LabVIEW. We added text-based math with .m files, and then continuous time simulations for things like feedback loops where you need to AGC and things like that. And then the state charts where some application. That's a more immature technology at this point. All in the LabVIEW environment, in one environment where we're programming multi-core computer processors, we're programming FPGAs, and in some cases, as I put it now, we manage GPU cores. You still have to use your own routines, but we can manage where the computation is done. On a choice of platforms, a combination of platforms, so this creates a very, very powerful real-time development environment. Now, we've also worked with university. This is some years ago. We got started with this example. Doing 4G MIMO, so we've come away with now with 8x8 MIMO, I think. But it was a good start. We learned a lot, and these pioneers got a few arrows in their back as we were learning how to make all this stuff work. That's kind of the nature of this as you're just getting started. Here we have an example of interference alignment research going on here at UT. Another example at Virginia Tech at cognitive radio. We heard a lot about cognitive radio today. We're very actively engaged in that with our FPGA technology as well. Here we see a cooperative MIMO receiver at Berkeley that we're working on. So using this technology for research applications and as well as the test applications, demonstrating this space of design and test as we go forward. So that's a little quick overview, National Instruments, and what we're doing in the communication space. So I guess we could open up for questions.